E. All right. Missed everyone's. 4, 3. Okay. We have 4 lectures left. So today is weather forecast. Next week is climate. The following Tuesday will be panic. Or thermodiagrams due 9:21 a.m. Final Tuesday. Okay. So I'll make sure I'm around as much as I can be. Next week was pretty good on the calendar. So do try and get in if you need me to look at the thermodiagram. Be a good one. All right. So we talked just a little bit on Tuesday about numerical weather prediction and this whole idea of looking for patterns, right? And so this morning I want to walk you through these 2 components. One is a little deeper into how we go about making forecasts, right? How to interpret these particular maps and what they mean. And then at the end, I'm going to, I don't know, maybe 15 minutes at the end, talk about operational weather forecasting. Okay, how we then take these computer models and modify them depending on a number of different conditions. All right, so how do these models work? I think I made the point on Tuesday that these are enormously hungry from a data perspective, right? We're talking about multiple connected supercomputers that are able to do something like 10 quadrillion calculations in a couple of hours. Our computing power at the moment, even though it is rapidly developing, obviously with AI, and how AI will play out, certainly it will be part of this rapid build out of infrastructure to support things like weather forecasting. The models will improve, our computational ability will undoubtedly improve as we go through the next couple of years. But we're still limited by the sheer size and scale of what we're trying to do in terms of use prediction for not just a region like Texas, but the continental United States, and then models that take on the entire planet, right? We're limited as to how quickly we can get that data into these computers, and then how we go through those calculations. So the first thing to appreciate with computer predictions, with numerical weather prediction, is that they run on a grid, okay? So it's like taking the region. Let's say we're modeling the continental US, the lower 48. We have to have data to put into the model, right? You got to feed something into the model. The only way you can do this, right, with any sense of accuracy is to input all of that data into an organized geometric grid. It's like laying down a chessboard across a region, right? Like the state or the continental US. And it's like the floor here, right? We see all of these tiles. Let's say the US was laid out across the floor here, okay? We lay a grid down on that region, right? And the computations, all of the equations that are built in to describe the state of the atmosphere. So these equations that we haven't even touched in this class here, but things like the radiation balance, all the thermodynamic equations have to be calculated at a point, right? They can't just be spread randomly across an area. It doesn't work, right? And so these calculations that are done at a particular point within a very organized geometric grid, okay? And so that's exactly what these models do. They lay down, and I've taken these 2 on the left here, I'll explain what those mean in just a second, but they lay down across the US this grid, okay, on top of a particular area. The challenge is, the more grids there are, in other words, the finer the resolution, okay, the much more complicated the modeling is. It takes longer for the computations to actually work, right? Because it's just a question of computing power, right? And resolution of the data. So for example, you may have an area where we've got 9 squares here. Here is the grid. Okay, and the center point of each of these squares is what we call the node, right? That's the node of each square. And if you had one big square and you were laying it down across the entire US and you had one node, well, that would be easy. You'd have to just solve all of the equations for that one point. But then you would have no data on either side of that. You can't do that, right? You can't release a weather balloon in Denver, take all of that data and model all the data for Denver and then say, okay, I'm just going to produce a forecast for the whole of the US. From Denver, it doesn't work. Like you've got to have as much data as you can spread geographically across the whole region, right? I mean, that just makes sense, okay? So the fewer the nodes, right, the easier it is, the faster the computations, you can make those calculations more quickly, but you lose resolution, you lose confidence, and the system doesn't really produce anything meaningful. Unless you've got a completely unrealistic situation, like one gigantic high pressure sitting across the entire US, well, then that would probably work, right? But when you've got a real life situation, which of course is such a dynamic atmosphere, it doesn't work. So as you start increasing the resolution, right, as you start putting finer and finer grids on top of a region, you increase the resolution, you get much better model output, right? Your confidence goes up dramatically in terms of your weather forecasting, but it takes much longer for those calculations to run. Very limited as to how far out you can go before you've got to do the next set of calculations. Does that sort of make sense, right? So this whole notion of grids is a really important kind of framing or context with the computer model. So what is the resolution of the grid? And I'll show you a couple of models and just introduce you to how those two grid sizes change and what they actually mean. Okay, the other challenge, there are many challenges here, right? The other thing is these computer models are not done from a grid just at the surface, right? They'll put a grid on the surface, and then most of the models will have somewhere in the region of 60 to 70 grids going slice-wise through the atmosphere, right? So you're not just solving the equations for the surface and having all of these nodes talk to one another, right? And interpolating between those nodes. You're doing that for the surface, and then you're doing it 10 meters off the ground, 50 meters off the ground, 100 meters off the ground, all the way up to probably something like 200 millibars, right? 12, 13 kilometers up. Does that make sense? So it's an incredibly nested, complicated surface grid. And then you've got like, oh, just another 70 of these things going up vertically. All of that then has to be, all of those equations have to be solved, right? So computer modeling, especially when it comes to numerical weather prediction, is always a trade-off between the resolution, okay, and the computing power you have, and then how far out you can actually go. And I'll add a little bit more detail as we go on this morning. But that's the first idea. That's the first concept, is this notion of it. Okay. All right. So a nice little simple graphic here that I've taken from the NOAA website. This is a nice conceptual diagram of how the modeling process works, right? So you've got your grid, okay, and just as a frame of reference, the main model we'll talk about this morning has a grid of 12 kilometers, right? So it's 12 kilometers by 12 kilometers. That's the scale that we're talking about. So between here and DFW, you've probably got, what's that, 3 miles, 25 miles, so you've probably got 3 nodes that are being computed down I-30. That kind of makes sense, right? So you lay your grid down, and then you introduce your first potential error into the model. And that is, before you can run a model, you've got to have some input. Right? You've got to have what we call the initial condition. What data are you putting in to each of those black blobs on the previous diagram, right? So on this one here. Whoops. So if we're going to start solving all of the equations at the surface here for dew point, vertical velocity, pressure, advection, energy balances, what data are we going to put into that blob right there? And then what data are we going to put into that blob and that blob, right? And we've got to have all of the input data before we can even click run, right? Or we can even get the model to produce those calculations. Now we don't have, so the model we're going to talk about has this grid of 12 by 12 kilometers. Okay. We don't have weather recording stations across the entire US every 12 kilometers, right? We've got one at Leacham, we'll have one at DFW, we've got a few weather nodes around in Metroplex that are measuring rainfall and sunshine and stuff like that, right? But it's quite concentrated in these urban areas. But what happens when you start driving out west, or you start going out into rural areas, right? You don't have the input data. Okay, so that's the first point. And the second point is, remember that we do send up weather balloons, right? We've got these soundings that are going up every 12 hours. Okay, and right now in the US we have, I think 90, is it 92? It's 92. 92 locations that are sending up weather balloons every 12 hours, right? So we take the entire US and we have 92 locations, and only twice a day do we have data first, right? See the problem here? We've got this grid that sits on the entire US, bless you, every 12 kilometers, but there's enormous data gaps, right, between these nodes. Okay, so you've got a grid here that has a node. You might have a grid here that has a node, another 12 kilometers down. That's cool. So over 12 kilometers, you've probably got some good surface data. But you may, if you're lucky, sitting in an urban area, you may have one weather balloon released here, and the next one might be in Houston, okay, or El Paso, right? So that's the first big potential error into the computer models, is you've got to put all of the data into each one of these little black nodes, okay? But you don't have the data to put into those nodes. So what are you doing? You're interpolating between the nodes. So if I'm a node in DFW, right, and we'll put Emma back home in Tulsa over there, right, and say we're releasing two weather balloons, it's a pretty large distance, right? But all of the data, all of the weather data, the dew points, the temperatures, all of the stuff, you may have one set of data, I've got another set of data, and everything in between has to be interpolated. Does that make sense? It has to be estimated. So the point here is the initial conditions, as good as they are for a continental US situation, are extremely data sparse when you go over oceans and obviously other countries that don't have the infrastructure to release weather balloons and so on. That's just, it is what it is. We don't have weather balloons being released every 12 kilometers. That would be cool, right? Be a lot of weather balloons. It would be extraordinarily expensive. But your starting data would be great. Okay, so that's a problem. But yet there's no way around it. You have to start the computer now. Having said that, over the decades, we've gotten really good at reducing error and seeing what the interpolation is like between Zaya at the back, Jackie and me, and you guys around the room, if you all represent the United States. Over time, we've reduced the error. But there's immediately error in the initial time setup. Okay? So a computer model is initialized, and it's you'll see that that's the initial step. So there's the initialization, and on each of the maps you'll see when was the computer model initialized? In other words, when did the meteorologist hit the enter button and start the run? And then it will say this forecast is valid for X number of hours down the line, right? And these computer models, bless you, they'll put out a valid number for 6, 12, 18, 24, 30, 36, 42 hours as you go down the line. Okay. So there's the initial time step, right? Then you run it through the supercomputer, okay, and in a few seconds, boom, it spits out this, which is known as a prog. And the prog is a prognostication. It's a map. It's a forecast map of some future state of the atmosphere, right? So let's say you set your computer model up and you say, I want to run this computer model to produce a forecast map for an hour. What's the next hour look like? Okay, and it'll do all the calculations and it comes back really, really quickly. Okay, there's not people sitting behind the computer with little calculators doing all the calculations. It's done like that, right? So it produces the prog an hour down the line. And then how does the computer model then make a forecast for, let's say, 3.5 days out, 84 hours out? It takes that prog and it uses that as the input for the initial step 1 hour later, right? And then it has all the readings, does the calculations, produces a prognostication for 2 hours down the line. Then it takes that map and feeds all that data into the computer, and it goes through another set of calculations. Does that make sense, right? So all the time, as we're moving down through this loop here of producing a forecast, pumping it in as this setup, producing a forecast, each time that happens, again, there's the potential for mistakes and errors, right? Because you're taking a prog, say 12 hours from now, so we take a surface chart from, let's round it down to the hour, 8 p.m. this evening, right? Well, we don't really know what the atmosphere is going to look like by 8 p.m. this evening. We have a pretty good idea, depending on the status of the atmosphere, but you're using that data to then produce the 9 o'clock map, and the 10 o'clock map, and the 11 o'clock map, right? So what does that all mean? It all means that weather forecasting is never, ever, ever going to be absolutely perfect. It cannot be. We've introduced way too many problems right up front. I know that's the depressing news. The good news is that we're still pretty darn good at it, okay, because of the way in which these equations work. Right? And so what we have then is this thing, this whole thing runs. I don't know how long a full run takes. I'm guessing probably 15 minutes to do all of the calculations and to produce the forecast. Okay. And then that runs for 70 layers. Okay. And what it does is it produces, there's nothing on this slide that's going to end up in an exam. This just gives you a visual for what this actually looks like, right? You've got the surface map here, and you've got surface temperatures, and you've got the wind. And then that computer is mapping the 3D clouds, right? What the moisture profiles look like, and it's building up a picture of the 3D clouds. It's looking at the upper levels, it's giving you the wind, and so on, right? So it gives you this 3D look into that particular system, and then the next hour it pumps it out and it keeps doing that, right? It's extremely complicated, which is my plea for you guys to give the weather people a break when they don't have absolutely perfect weather forecasts, because we're at the limit of what computers can do all the time, even though the forecasts are actually remarkably good. So some state of the atmosphere in the future looks like this, right? This is what a prog would look like. This is directly out of the National Centers for Environmental Predictions. And just down here, I know this is small, but I'll read it. It shows this is the 12-hour forecast of fronts, pressure, and weather. This is a very general prog, right? Then there's ones of the upper levels and everything. I'll show you exactly what these look like, right? But that will be the future state of the atmosphere. And then that becomes the input for the next iteration of the model. That runs through iterations. So that's the kind of the framing of numerical weather prediction of how this actually works. Does that make sense? Okay. All right. Whoops. Misbehaved. Okay. Love. Does anybody have the? Do you have the PowerPoint up in front of you? Have the PDF up in this? Are you looking at the? Okay, good. I just wanted to double check that I uploaded the right one because I made some changes to this.
What's like the baseline prog? Like, does it have like a certain height that is the? Oh.
Yeah, we're about to get to that. There is. We're about to get to that, right? It's called a full panel prog. Good question. Yeah. If it doesn't answer your question, then throw something. All right. So here's an introduction to the most widely used one. So this is from Tropical Tidbits. Again, remember, depending on the website that we look at, you'll get different graphs, whatever the case may be. And I'll go on and take a look. And so this is one of the computer models. This is called the NAM model. So this is the North American Mesoscale model. Okay, this is the one that is the most widely used here in the continental US and in Canada, right? The North American Mesoscale. And you can see here, so when you look at the upper bar here on this website, it says mesoscale, and this goes straight to the net. So the North American Mesoscale. It is a very high resolution model, okay? And the grid here is 12 kilometers. So that's why I use 12 kilometers on the example here, okay? So it's a 12-kilometer resolution model, okay? And it produces a forecast out to 84 hours, right? So that is 3.5 days. That's as far as it can go because it has so much data in it and because it's got such a high resolution. So when you look down here, okay, these are the 1 hour forecast and it goes down to 84 at the bottom, right? So that's the longest out. That's the furthest out, not the longest. That's the furthest out that this model can go. 84 hours, 3.5 days, right? It has 60 levels in it. Okay? So it's got 60 slices through the atmosphere. And it's integrating up and down through that atmosphere. There is, that you don't need to know this specifically, but I just wanted to throw it out there to be complete. There is a version that's called the HRRR, okay? And that stands for High Resolution Rapid Refresh. So within that model, there's a NAM on steroids that you can do a very rapid refresh, and it works on a grid that is 3 kilometers. So it's super high resolution, but it can only go out about 18 hours. You don't have the computing power, or the error becomes too great as you go out for 18 hours. I mention that because they use the 3-hour high resolution rapid refresh to really try and nail down thunderstorms, right? Because think about 12 kilometers times 12 kilometers, 144 square kilometers. You'd go down to where? Arlington, maybe something like that, right? You go down to I-20 and probably the north end of 121, something like that. You can have a thunderstorm pop up right in the middle of that the NAM would miss completely, right? Because the storm, we know that storms can be individual cells. So they were also running this short-term high-resolution rapid at 3 kilometers. So what you've got is you've got a 12 by 12, and then you've got 3, 6, 9, 12, 3, 6, 9, 12. You've got little squares within that then starts picking up. Hang on a second, it looks like there's a small thunderstorm here. Does that make sense? It does give you a better look. They only use that for convection, for small-scale convection, to try and increase the predictability. It is run every 6 hours. Okay, so the NAM is initialized, all the data comes in, and then it's run every 6 hours. So midnight, 6 a.m., midday, 6 p.m. is when it's run. Okay. And then just some description here around the NAM. So it's short term, 3.5 days. So clearly we don't use NAM for a 7-day forecast or a 10-day forecast. So it's short term, high detailed forecasting. Okay, it's pretty darn good, 0 to 2 days out, right? So incidentally, when you start seeing severe thunderstorm warnings and watches come out, it's almost always from the NAM model. It's pretty good at convective activity. That's when they bring in the 3 kilometer resolution one, right? And it's good at severe hazards like snow or severe weather. So NAM is what the majority of forecasting is done, right? And this is an example of an output. This is not the baseline prod to your question. This is just one of the maps, right? But I'm pulling this up just to show you, and I did this. This was initialized at midday Greenwich Mean Time, so that's 6 a.m., April the 13th. What is that? April the 16th. Oh yeah, I did this on Monday because I thought I'd get to weather forecasting on Tuesday, which I did. So this was initialized at 12Z, April the 13th. This was forecast for 1 hour, right? So this is the 1 hour forecast, valid at 13Z. right? So this was just the 1 hour prognostication for 13Z. And what is it showing? This will always be on the maps. And just incidentally, guys, on the final exam, and especially when it comes to the integrated assessment, right? You're not going to have to guess what these maps are. I'm going to tell you specific. This is the output. This is when it's valid for, right? So you'll know exactly what you're looking at. So this is the North American mesoscale, 12-kilometer grid resolution, 500 millibar heights. You now are pros at that, right? So that's the black lines, the 500 millibar heights. This is 570, so 5,700 meters, right? And DAM is in decameters, so it's missing 0. And, our old friend, vorticity, cyclonic vorticity, okay? That's the scale on the right, the red scale in the vorticity. Don't worry about the units, 10 to the minus 5 per second. And then the wind knots, right, or the wind bar. So you're looking at, you won't have to guess. You're looking at the 500 millibar chart. It's showing the areas of vorticity, and it's showing what the wind is. Does that make sense? So that's what the output looks like, okay, from the North American mesoscale. Okay. All right. I don't know why this is misbehaving today. So how do we go out beyond 3.5 days, right? Well, we can't use NAN. But we do use what is known as GFS, right? So GFS is the global forecast system, okay? And it goes out 10 days. Initially, and then it goes out another 6 days. So it goes to 16 days. This goes out just beyond 2 weeks, right? Don't worry about the 12 kilometers there. That's a very unique situation. The grid for the GFS is 28 kilometers. So it's a bigger grid. They've got more than less than half the calculations to do. Okay. And that's only for 10 days. So for the first 10 days, it's operating on a grid that's more than twice the size of the North American model. And then from 10 to 16 days, because things really start becoming much less certain, it actually broadens that out so we can get through all of the calculations to 70 kilometers. So the grid starts increasing on the GFS. We may get a point where the GFS runs at a 12-kilometer grid every hour and the computers can handle that. We can't do that. We're not there yet. Right? This is an incredibly data-heavy, intensive system. It too is run every 6 hours. So 0Z, 6, 12, and 18. It's run out to 16 days. And this is a long-range plan model, right? So we're looking at more than 3 to 4 days out. Okay. It really focuses on the jet stream and what the upper levels are doing. All right. We're not trying to resolve a multi-cell clustered thunderstorm sitting over Florida 7 days out. There's no way we can do that. Right. They take a step back and look at broader resolution, specifically in the jet stream. So it's the same map here. This was initialized at 6:06Z on the 13th. So this was actually midnight on the 12th, Sunday night. The forecast hour is 384. This is now valid for 06Z, Wednesday, April the 29th. I'm going to come back I'm going to come back on the 28th, our last day of class, and we'll pull this back up and see how close they came. Okay, so we're going out 384 hours, 16 days, right? Don't plan a wedding or a round of golf based on the 16-day forecast, right? Depending on what the jet stream is doing, you could be badly wrong. Could be pretty close, okay? And you can see it just cuts off down the bottom there, the 385 hours goes below there. Does that make sense? That's the same thing. We're solving these equations through various layers. We're just doing it at a much greater resolution. A bigger scale. And so that's the only way the computers can handle it. All right. So this comes to your question on what is the standard prop. So if you're in weather forecasting, and I know that we did this I know it's been a long time now, but the TV stations still do this. The first output that comes from the National Weather Service is what is known as a 4-panel probe. That's the initial thing that gets spit out. Okay, that comes out. It's 4 panels. We don't look at one, we look at 4 different panels. Okay, the 4-panel prog. And so let's introduce you to what a 4-panel prog looks like. All right. So these graphics are not the ones we're going to use, but I just think they're quite colorful. That's a 4-panel prog. This is like exam 3, question 7. Here's a 4-panel prog. Knock yourselves out. What's going on here? So there are 4 panels here: top left, top right, bottom left, bottom right. These ones show, and not every one that comes out is exactly the same, right? Some forecasting centers, some TV stations, some FEMA organizations like to look at slightly different components of the 4-panel prog, but it comes out looking like that, right? And these are, and the thing about the 4-panel prog is you've always got to look at what the initial time is. Okay, so this is what it looks a little bamboozling because this is actually how it comes out. So the initial time is 180103, right? So this is 1800 hours on the 3rd of January. I'm not going to ask you to decipher this in an exam, right? So this the initial time is 1800 hours on the 3rd of January, all right? And this is the 12-hour forecast that is valid 18 hours down the line. It looks very bamboozling and confusing, but each prog has exactly when it's valid for, right? Again, in the integrative assessment, I'm going to give you that. I'll give you a printout saying these maps are valid for exactly these times. Okay. All right. So let's look at 4-panel prog. So the first, and this is common, right, on a 4-panel prog. The top left is almost always the 500 millibar surface, right? And that's why I've said like a beaten this little drum throughout this course. We go to the 500 millibar surface almost always. So this is what the 500 millibar surface looks like. Okay, it's from the previous slide as well to be consistent. So this is the NAM, 12 kilometers, 500 millibar height, vorticity and wind, and it's valid for 14Z Tuesday, April. So this was valid. I did this because I thought I would get to this on Tuesday, and we'll take a look at what the ones actually look like this morning in just a second. But this was the Tuesday morning, 8 a.m. as you all walked into class. Right? This is what the forecast looked like. So 500 millibar height, so the dark contours, and the isovorts, the lines of equal vorticity of spin at the 500 millibar surface. Okay, so that's the first panel. It's almost always that, and they've got the wind on there as well. So you can see on Tuesday morning there was a prop here, right? Highest vorticity over here, nice divergence over Texas. Not much going on, at least over our part of it. So that's the top left panel of a 4-panel prog. Okay. Top right panel is almost always, so consistently, a sea level pressure. So this is exactly the same time, 12 kilometer MSLP, mean sea level pressure in millibars, and the wind speed in knots at 10 meters off the ground. Okay. Some frogs don't do 10-meter wind speed, some do vertical velocity, but this is a very common way to look, right? So we're looking at not just what the upper levels do, but we're looking at surface pressure. So there's a low here, here's the high. You can see all of this flow is wrapping around the high. So this is all the influx of fairly warm, moist air, and that shows you the wind speed. So we've got 500 millibars and vorticity, surface pressure, and wind speed on the top left and the top right of the 4-panel prog. Okay. So this is sometimes, so the text on the top right there is the same as the previous slide, but the reason why I've laid this on here is that sometimes, and actually some people really prefer this, is that instead of just looking at the surface pressure, they'll put a surface pressure map, and then they will put not the wind speed, but they'll put thickness. And I wanted to talk a little bit about thickness because it actually is super important. Okay, so this is a map, right? We're looking at the same thing, valid. This is actually valid 1 hour later. So this is 15Z on the 14th, right? And we're looking at the thickness in decameters, right? It also shows precipitation type, and this is surface pressure. So there's that surface load. I'm going to go back a second just so you can see the consistency here, right? Here's the surface load. So the surface pressure map looks the same here because it is the same. I know it's just a slightly different scale, and we've got precipitation type, but it's the dashed lines that I want you to focus on here. It's the thickness. Very important concept here in the modeling. So what is thickness? Okay. Again, just look at the numbers here. So this is 5,700 meters, right? This is 5,400 meters. And there's a reason why there's red and blue on the thickness. So the thickness is the height between the 1,000 millibars and the 500. So what it's saying is, let's not worry about all these individual surface pressures. Let's just look at the pressure, the height at 1,000 millibars. So they go to a constant pressure surface, really close to sea level, right? So probably 10 meters up from sea level. And what's the height of the 500 millibar surface? And how thick is that? In other words, it's asking the question, right? Where are there tall columns of warm air? And where are there short columns of cold air? That's what it's asking. Okay, and this is what thickness looks like in a side view. And this is why it's so important. Okay. So on the top here, we've got warm air. You've seen a diagram like this when we talked about upper levels. So when your air is warm, your height thickness is large, right? The physical distance between the 1,000 millibars and the 500 millibars is greater than when your air is cold, right? The thickness is small. Make sense? Tall column of warm air, short column of cold air. I didn't think you'd have to come back and think about that concept, but here we are, right? And the reason why it's so important and why meteorologists look at thickness is you can calculate what the average temperature through that tall column of warm air is and what the average temperature through the short column of cold air is, right? And here's two examples, two kind of endpoints. When your thickness is 5,700 meters, in other words, when you've got a greater distance between the 1,000 millibars and the 500 millibars, your average temperature through that column of air is 8 degrees Celsius, not minus. It's positive 8 degrees Celsius on average. In other words, if you sent your weather balloon from the surface here and it went up to 500 millibars, your average temperature would be about 8 degrees Celsius through it. It would obviously be warmer at the surface and it would be colder aloft, right? But on average, it's a tall column of warm air. Okay, but when your thickness is 5,100 meters down here, your average temperature through that column of air is minus 22. Right? That's why thickness is so important. Meteorologists look at how thick, how deep is the tall column of warm air, right? And how, Honey, I Shrunk the Kids, how short the short column of cold air is, right? And the bottom line to all of that is that the 5,400 meter line is the line that almost always demarcates liquid precipitation from frozen precipitation. Right? So that's why on this map, it's colored in blue. So this is the key line that meteorologists look at. Okay, frozen precipitation from solid precipitation. Does that make sense? It's not absolutely perfect because there's variability and there's individual snow and rainfall, sleet and mix, right? But generally speaking, down here, this is going to be liquid precipitation, and anything above that 5,400 is going to be frozen precipitation. There are exceptions depending on elevation, right? So here we've got some snow here in the mountains, but generally speaking, we've got liquid here and frozen above, or some sort of mix above. Again, it's not perfect, but that's the line that meteorologists look at. So we look at thickness as an indication of how cold that air mass actually is. Does it make sense? What are your questions? Okay, cool. So that's the prog. A couple of other maps that go onto the 4-panel prog. So generally upper levels, vorticity, surface pressure. Question.
Sorry, I do have a question.
No, good.
Back on the slide you were just on.
This one here?
Yeah, with the blue line,
Yeah.
which is the red. So like, is that just saying that, or sorry, the other line?
This one here? No, we go back another one. Yeah.
So the blue, so if it were to rain in that area, it would be frozen?
It would probably be frozen or some mixture.
Okay.
Right? And again, you can see it's not perfect because when you look at here, the snow is the blues and the purples, right? So here's the 540, and the 540 comes down there, and there is some liquid on this side here, and there's some frozen on that side there. It's not like the 540 goes, okay, it's all rain here and then it's all frozen here. There's some give and take there. But that's where they look at things like freezing rain and sleet. Okay, good question. All right. So top left is upper level 500 and vorticity. Top right is surface pressure and winds, but often thickness. Bottom left depends on what they put in here. More frequently than not, on the bottom left of a four panel prod, I see this one shows mean sea level pressure, right? I see relative humidity most frequently in the bottom left. Well, this one does have sea level pressure, and then it's got relative humidity as a percentage, right? The relative humidity can be, the prod can be, this is the relative humidity at 700 millibars, right? But this one I like because it shows the relative humidity between 300 hectopascals and 700, right? So remember your thermodiagram. The mandatory pressure surface is 850. Why? Because that's generally the lifting condensation level. 700 millibars is a key mandatory pressure because we're kind of in the guts of the storm there. You're probably in that super cooled water area. And of course, 300 is the jet stream. So what this is showing you is the relative humidity through a deep layer, right? And that's what you're interested in. Okay, so here the relative humidity is very, very low through that deep layer. Here the relative humidity, we're up in the 80s to 90%. So you'll overlay the relative humidity, that gives you the moisture content. You put the 5-4 line on there that tells you how much snow or how much rainfall you're likely to get. It's a very common part of the 4-panel prod, is relative humidity. Through depth, okay, and then the bottom right varies quite a bit on what they put on the 4-panel prod. I often see 24-hour precipitation. Sometimes they do 6-hour precipitation, but they'll do 24-hour precipitation. Okay, these are all the same maps. So what's the accumulated precipitation likely going to be? Or I suppose, you often see our old friend, hey, convective available potential energy, right? On the forecast models, they're not counting up the boxes and multiplying by 5 like you guys are doing in the thermodiagram. They're expressing it, and it's also in that handout that's online. They're expressing it here in terms of joules per kilogram. So this is convective available potential energy. And anything in the reds and purples here, this is where the greatest convective potential is. So that's where they will start merging. Precipitation, convective potential, relative humidity, where's the divergence, all of that good stuff, right? Begin to build up the forecast. I think that's as far, we're not going to stop now, but that's as deep as I want to go on the modeling, right? So that's just one model, okay, as a set of output from the North American mesoscale. Let me, just for a second, I know this is a bit jumpy here, but I'd like to, let's just go online here. You know what? Let me go to pivotal weather, just so you can see. So pivotal weather, yeah, we'll go. So when you go into pivotal weather and you go into models, right, and you hover over the model, I'll just show you this. Okay. If you're like super interested in modeling, knock yourself out, right? These are all the models, but here's NAM. So this is the regional North American mesoscale, right? The various other ones. There's the HRR, right? The high resolution rapid refresh, but actually this is the high resolution rapid refresh at 3 kilometers for the continental US. You can go into all of these other ones. Here's the global forecast system, the GFS, which is the 28-kilometer grid. And when you go to 10 to 16 days, it's the 70-kilometer grid. This is another one that you'll see often referred to on television, right? They'll talk about the European model. Okay. You may have seen that or may have heard that, the European model. This is an excellent model. Actually, it's better than the global forecast system, but the Americans just want no part of it. So they stick with the GFS, but the European ECMWF is the, oh gosh, it's the European Center for Medium Range Weather Forecasting, right? So it's a bunch of Brits and French and Italians, Greek sitting there modeling the global forecast system. It's very, very good. Actually, what the Hadley Center in London does, and the National Centers for Environmental Prediction in the States, and also other global centers, is they're all communicating between here's what the European model says, here's what the global forecast model says, and they're looking at what is the degree of convergence between the two. I'm going to come back and talk about this in just a little bit, right? Ensembles, don't worry about that. Okay, so that's what it looks like. But when you look at the models, right, this is a slightly, they have slightly more information here. We've got surface, and you can just look at the variety of things that come out of this model. It's not as simple as a 4-panel product. It's not just those 4 panels. It's multiple things that go on here, right? So we've got 2 meters above ground level temperature. We've got the dew points, right? We've got 10 meters above ground level. We've got the 6-hour QPF. That's the quantitative precipitation forecast, all the way to 48 hours. That is just the surface, right? Then you look at our old friend, the upper air. Oh, very cool. So it breaks the upper air out here. We've got 500 millibar heights and winds and temperatures. Then we've got upper air dynamics. All right. These all come out every 6 hours. This includes advection and vorticity. And this is the one I like spending a little bit of time on, just because I'm a bit of a dork. But here's the severe weather, right? These are all the severe weather prods. So we can't have an 84-panel prod. That doesn't work. Those are the 4 main ones. But then when you start looking at resolution, we've got, what is the K? Oh, here's one, mixed layer convective inhibition. How much inhibition is there? That little orange area that you guys are going to color in, right? On your thermodiagram. What is the storm relative helicity? Oh, nice, right? What is the horizontal spilling that the model's putting out at that 12-kilometer resolution? So it's extraordinarily complex coming out of the model. So we're just scratching the surface, okay, in this class. Okay, so let's go back here. So what does that all add up to, right? What it adds up to is this, what you get on your app. And I don't know what app you use. I've got 12 better apps on my phone, okay? So when you're looking at a forecast, you're going to look at, generally, you're probably not going to cut it out into what's the 1-day forecast, the 3-day. You're going to say, well, what's the next 7 days, or what's the next 10 days? So now you know that that forecast is a combination, right? And I hope someone asks you this over Sunday. So then you used to the weather and climate, of course. So what goes into a 7-day forecast? You can say, well, the first 3.5 days are the North American mesoscale. And then the next 10 days out are the global forecast system. But it's all collated into lovely graphics, depending on who you look at, right? Weather channel, channel 8, channel 11, whatever the case may be, you'll see what so the 24-hour forecast, the 7-day forecast is a mixture. It's a combination of the North American and the global forecast system, and probably the European model. Anything beyond 7 days, yeah, it's the global forecast model, but your error bars start doing this, right? It starts becoming a little bit of the thumb suck, as I've said to before. So how do we go out? What's another way in which we can look at modeling? Okay, we cannot approach it from a grid perspective. Okay? So we can take the whole grid away, and that's where this comes in. And I just want to introduce you to. I love these diagrams. These are known as spaghetti diagrams. Okay, so this is ensemble forecast. Okay, ensemble forecast. And what you're doing with ensemble forecasting is you really are looking at the upper limits. You're looking at 500 millibar surface. You're looking at the 300 millibar surface, the 250, depending on where the jet stream is. Okay, so you're mapping out what the jet stream is doing, not from a grid perspective. So you're not solving equations at little nodes, right? But you're using a completely different modeling approach, right? You're modeling sine waves. So it's a mathematical modeling where you're looking at how the waves are changing. You're not integrating across 12 or 28 kilometer grids. There's no ways we can do that, right? So this is the output of an ensemble forecast, okay? And it's from the global ensemble forecast system. And there are 20 colors here, and each color is the starting initial point with slightly different input conditions, okay? So you're not just putting all your eggs in one basket, and you'll see why in just a second. So you're starting this model and you say, hey, dear computer, this is the starting point of where the jet stream is, right? And what you're looking at here is this cluster here is the 5,700 meter height, right? And you can just see that in the top there, 570. And this cluster here is the 528 height. So what you're doing is you're telling the computer, let's look at what the tall column of warm air is doing and what the short column of cold air is doing. Does that make sense? Right? On the thickness diagram, the question that Emily asked was 5,700 and 5,100. Here they're going 5,700 and 5,280. Let's just give it a bit of a nudge upwards. So they start the computer, right? So this was an output on the 11th of August, 2006, right? And this was valid. It was started at 1200 hours, and it's valid for 36 hours down the line. So this was a 36-hour forecast. It was initialized at midday, Greenwich Mean Time, right? On the 11th of August. Oh, that's my kid's birthday. Maybe that's why I did it, right? So the computer started on the 11th of August. They started with 20 slightly different initial conditions, bumping some things up and bumping some things down. They hit enter and they said, tell me where those two height contours are going to be 36 hours down the line. Does that make sense? It's an ensemble, right? And they take that whole cluster and that's what it looks like. So you can see that this computer has very strong agreement 1.5 days out where that height contour will be. And especially if we look at West Texas here, okay, that's the spread. It's not insignificant, right? In other words, that 5,700 meter contour height is somewhere between there and there. In Texas, that's I don't know what that is, 100 miles, something like that, right? Not bad. It's never perfect. It's even tighter here, right? But here, if you were trying to make some forecast for Juneau, Alaska, right, where's that 5,280 lie? It's starting to get a bit wide. Does that make sense? And this is why we will never have perfect forecasting. So just to see what these look like, this is 36 hours out. It's 108 hours out, right? These were all started. I'll just go back a second, right? So this is valid on the 11th of August. This is now valid on, sorry, these were all initialized. Okay. Whoops, going back. So this is valid 108 hours out. Canada, knock yourself out. This is valid 228 hours out. This is the 10-day forecast of what that tall column of warm air looks like, right? Yeah, there's convergence here, not strictly convergence, but there's some agreement here. But depending on your initial conditions, you could have a closed off low here, or you could have something over Nebraska. Awesome. I mean, how do you make a forecast based on that? It's very, very tricky. Let's go a little further out. 372 hours out. Okay. Yeah. So this looks like a 3-year-old with a crayon. Okay. I mean, this is all based on slightly different initial conditions. What's 372 hours out? 16 days? Is that something like that? 15 days, right? So this is the challenge with long-term forecasting. It starts becoming extremely problematic. But that's kind of where we are. When we start going out even longer, okay, we have no way, obviously, of modeling that what the jet stream is going to do in the very, very long term. We can only make estimates based on long-term probability. So when we see maps like this, right, this is the 3-month outlook where temperatures are going to be, there's a 50% chance temperatures are going to be above normal here. There's a 40% chance they're going to be below normal there. That's a broad estimate based on long-term jet streams, El Niños, big-scale circulations. But again, we are nowhere near increasing the resolution of it.
This is like besides the point. I don't know if this is just but the Apple weather app, especially this week, it's been lying to me. Yeah. Either it'll say it's gonna rain and then it doesn't, or it won't, says it's not gonna rain and then it starts drizzling like that.
Yeah.
Which
So why is it lying to you? So answer that question from a scientific weather climate. That would make a nice sense. Specifically for M3. Yeah. So why is it lying to you? It's not lying to you. What's the problem? Is there some drunken meteorologist that just wants to mess with you? No. Hey, think about what's going on outside right now. What the weather this week will be. You'll probably go and look at some maps in just a sec. Okay. Is there a big high pressure system that's predictable over Texas at the moment? It's the SIR, right? We've got moist air, we've got severe weather that's sort of in place across the Midwest. You guys have been seeing that, right? What's been going on across the Midwest and the upper Midwest, right? This is a really tricky situation to try and forecast because there's lots of things going on. Where is the cap? Where is the trough, right? How much warm air advection is actually coming in? It is amazing how badly wrong it can when the atmosphere is really disturbed. And I hate to use the term, but it's true, unpredictable, like it currently is. Good question. Yeah.
Is there a favorite like weather app you have that you think is most reliable?
No, I don't think there is. It depends on if I'm traveling or not. I use Windy quite a lot. Anyone seen Windy? That's cool. I use Weather Radar. I use a Norwegian site, YR. I use Storm Radar, Weather Radar, My Radar, Weather Pro, Rainview, Lightning Weather by PSC, NOAA Radar, and Ambient Weather. Those are the ones I have. Yeah.
You check all of them every day.
Now. Okay. All right. Let's just end off this morning with operation. This will be pretty quick and much more straightforward. Right? This is where we start using our experience and slightly more straightforward conditions where, because all of what we've talked about, all the maps, all falls under what is known as MOS, right? MOS stands for Model Output Statistics. The models are spewing out all of these statistics. We just are lucky that we have computers that will turn them into pretty maps, right? I'm amazed when I look back at some of the documentaries that I watch on World War II and the D-Day landing, right? And all those meteorologists that were taking ground-based measurements, no satellites, right? And standing with a big, huge blank piece of paper and physically drawing in the fronts and what they think is going on. And oh, just by the way, 300,000 people's lives dependent on your weather forecast, right? So that's a whole different story to operational weather forecasting, where we do have all of these model output statistics, but there are situations that are more straightforward, right? There are times when you have to modify the output. What are some of the things that models don't catch where you may want to modify it, right? So daytime temperature, for example. What is the duration and the coverage of clouds? Sometimes these models don't pick up the nuances and the subtleties, like exactly what's going on outside right now with cloud cover, right? Cooling from evaporation. Okay. These models don't really look at evapotranspiration and what's going on there. So that falls under a whole different area called hydrometeorology, the kind of stuff that Dr. Carell looks at. Okay, you may want to modify that, right? Sometimes there's not much departure from a 30-year average, especially in summer, especially here. Great, awesome, July the 27th. It's going to be hot and stinky. Same with July the 28th, same with July the 29th, right? You get into these patterns where there's not a long-term departure. So I wanted to bring this up. These are the monthly normals, the lows and high for the whole year. I circled Tuesday, but I'll just nudge these. They're the same numbers, right? The normal low for today is 54. The normal high for today is 76. Let me go on to one of my weather apps and see what it's supposed to be today. The normal low and the normal high. What's the departure from the means? The low today is 68, the high is 86. Okay, we are 10 degrees away from what the normals are. These normals are always averaged over 30 years, try and even out the high. I don't need to use a pun, but the highs and lows. So we are going to be 10 degrees above this, and almost 13 degrees above, 12 degrees above the normal low. Right? Why? Because we've got all of this low-level moisture coming in, which is making things a little trickier. Okay. So clouds and rain are important in controlling daytime high. Advection is important. That NB is my shorthand Latin for important, right? So advection is important in daytime highs, right? So you may have a forecast high, but advection behind cold fronts becomes really important in terms of how you modify your weather forecast. So you want to look at clouds and rain, you want to look at advection during the daytime in terms of highs. Cold fronts obviously are critical in terms of how you modify a particular output. So you may have a cold front coming through. So here's, you can see this is midnight, the temperatures are going up 4 a.m. and then the temperatures start dropping through the day. That doesn't kind of make sense, but it certainly does if there's a cold front coming through, right? So you're looking at how we take a computer model and look at some very specific regional changes to that. Persistence forecasting is lovely, right? That's when there's very little change. Okay? And that's when Emsley's apple will not be lying to her. If there's a big high pressure sitting here and it's ridged in and it's going to be here for 3 to 5 days, you're probably not going to be very far off the normal for a particular region. So persistence is interesting. But you certainly need to start adjusting your forecasts. Nighttime loads, radiational cooling is important. Remember that when we talked about one way to form inversions is radiational cook, right? So when there's no clouds, and you've got light wind, then your radiational cooling is rapid. But when you have clouds, then that changes the energy balance because you've got long waves going up and you've got much more long waves coming down. We come back to the radiation balance there, right? So a significant portion of that may come back. So cloud cover at night becomes very important in terms of how we modify global temperatures. And I think I'm just going to end on that. I know there's another slide. I think I just wanted to just some very broad general comments about some local regional things and how we modify that. Okay, you are now expert weather forecasters. Let's just take a quick look, as we've got time, as to what's going on right now. Let me pull up. Let's pull up tropical tidbits, lower dynamics. Okay, so here's the current situation. Surface pressure, 10-meter wind speed, initialized at 6 in the morning. And this is valid. So this is valid 6 in the morning. Let's see what the 36-hour one is. No, that's too far out. Let's look at 24. This is valid. What's today? The 16th. Let's look at 18. I'm back to 12. 12 should do it. Yeah. So this is midday today. Valid 18Z Thursday, April the 16th. All right. I think this starts talking a little bit about some of the complexity. Right. So again, all of this air is moving in. All of this air is moving up towards the Midwest. So we've got the influx of moist air. That's what's going on outside. Let's look at upper dynamics. 500 millibar. Do we want to look at the... Oh, let's look at vorticity. Beautiful. Right, so this is, and let's look at the 12-hour one, valid the same time. So this is the vorticity and wind. Right? This is a nice example, actually. I mentioned it the other day when we look at long wave. So here's a long wave trough here. Here's a little kink, a short wave trough over here. So there's some high spin over there. Very little going on across us at the moment. Some pretty nice geostrophic flow over the US at the moment. Okay. And let me go to pivotal weather because no, of course it doesn't. It's in a max. I don't know how to do that. Oh, well, doesn't matter. Let's look at another one. Let's just look at what the jet stream's doing. Upper air. There's the jet stream currently over the US. So when you start looking at these maps, I hope that gives you some sense of complexity of making what was it. Well, good, everybody. All right, next week, we're gonna change track. We're gonna do two things. Tuesday, we'll talk about long-term climate change, ice cores, Milankovitch theory, OEA. Thursday, we're gonna do anthropogenic climate change. See how we go on the final lecture. Make sure certainly drink coffee, but they do those on the All right. Good.
I saw you yesterday at the energy like thing.
Oh, did you go to the symposium?
And I was gonna see fine. Like,
Nice, Audrey. How long did you stay for? Were you there in the afternoon?
no, I left like.
Yeah.
What was that?
Yeah.
It was bad.
Right.
Yeah. That was cool. I learned about that.
Yeah.
My other son's
Really
cool.
Yeah. Yeah. I thought it was a good set of families.
Yeah. I got bored when they started bringing in like all the JP Morgans.
So financing isn't.
Yeah.
Like,
I know. They usually do lots of like finance, because everyone, I saw in energy business, majority like finance.
Yeah, I know Elizabeth, sorry, Catherine, she's really good at dealing with the microphone. But I don't know, I just find it dry. Yeah.
I just don't even understand it.
And we afford to do it. Yeah. I'm fine with you. Alright. Oh, my God.
Wait, is there any way you can go over a little, like a quick summary of what I missed on Tuesday?